proportional to the surface area of the patch, that constant will depend on the angles. So this term here is called it's called a differential cross section. So we're getting there, right? So we needed the concept of the solid angle, and now we're starting to talk about a cross section. In fact, this term here, this constant of proportionality between these two variables, so this is proportional to that, and the constant is this. This constant is called the differential cross section. Now, why that is, I can now talk on the second part. I need my little stool just a minute. I've learned not to trust the bed I fall off, so I sit on a stool. But okay. So, given that definition, you can rewrite this, the little sigma, as so just 1 over j dn d omega. Right? That's just a bit of algebra, just rearranging terms a little bit. Right? So remember this. Now, it's not as intuitive. Now it's called the differential cross section. Now the differential part's easy because here you're differentiating. So the adjective differential, that makes sense. But why is it a cross section? Well, I need to explain a bit more. There's still another stepping stone needed. Right? Now I mentioned a bit in the earlier session, but let's assume that our scattering is the target, the scattering center. Its potential, v, is a function of r, the distance r between the target and the incoming particle. Right? That distance r, and that's all. It's not. The potential does not depend on angles. Right? It doesn't depend on theta and phi. It depends only on r. Okay. In that case, this term here will not depend on phi. So you get a kind of. I mean, obviously it'll depend on theta, right? I mean, you're scattering. Most of the particles will go clean through. They'll hardly be scattered at all. Okay, so this here will be maximum when theta is nothing, right? And if you've got a severe scattering, like if the incoming particle hits the target dead on and then scatters right back, that's far more improbable than just getting a mild deflection or scattering. Okay, so this, if you like, the fraction of now n. What is n or dn? Dn here is the number of particles scattered through this patch. Okay, and if you divide that by the area, so you've got a differential between the number of particles through the patch and its surface area, the area of the patch here, omega. Now that, if you think about it, your n, that's going to depend on the scattering angle, right? I mean, the larger your scattering angle, the smaller the number of particles that will be deflected by that amount. Okay? So now this is a constant. J's assuming that's just the number going in. Let's say, right? So this you would expect to depend on the scattering angle. This will go right down as theta becomes large. The maximum theta is 180 degrees. It scatters right back. So that makes sense. But because of the potential depends only on the r. So the scattering angle theta, that is of relevance. But you'll get a kind of symmetry, like if your x-axis is the axis of symmetry of a cone, so imagine here's your cone. Let's see. So here's your cone, and the axis of symmetry of that cone is the line going through the tip, the top of the cone through. So that's your x-axis. So you can expect, just intuitively, you can expect a symmetry in the scattering that depends on this theta, but it doesn't depend on the phi in polar coordinates. So this here should just be this, just will be a function of one angle, not two. Okay, so you can rewrite this as this, and the phi. Yeah, the phi, theta and phi. Yeah, the phi here drops away due to the symmetry of the scattering. So you've just got this expression. This expression is called the differential cross section. Now I can explain why cross section. Here's your incoming beam, right, along the x-axis, and you get let's say you get a scattering this angle here. So imagine the particles scatter at this angle theta. So this angle theta is the angle between the x-axis and the scattering direction. Right? Now, because of the potential being a function of r only, you're equally likely to be scattered for a given theta in any for any phi, in effect. So you can find the dn here. Remember that's the here, where is it? dn, the number of particles scattered into a solid angle d sigma. It's dn by definition, right? 3 bars. The number of particles scattered into a patch of solid angle d sigma, right? Well, in this case, let the patch be this strip here of constant angle theta. So here's a unit sphere, okay, and this strip. So take your machete, take a melon of radius 1, and cut it twice. So you get a slice, very thin slice here of your melon. Now this surface, the surface of the sphere, of the unit sphere. So you've got this circular slice of melon, and let's say the melon surface is dark green. So you look at this slice and you find the area of the green of the slice, if you see what I mean. So it would be this surface area. Okay, that would be your d sigma, and your dn would be the number of particles that go through that surface area, that patch. Well, it's not a patch anymore; it's a strip, right? It's this strip that lies on the surface of the unit sphere. Okay, so that's the d omega, right? So for that d omega, this well effectively becomes infinitely thin, but this slice here, dn is the proportion of your j that goes through it, but we're dividing by j, so we're just talking kind of density, the unit, for a unit flux effectively, and that's how this is defined, right? And that little sigma is the differential cross section, right? So now once we have this, we could then integrate over all the solid angle, the whole sphere, and get something that's called the total cross section. And you may ask, why do that? That will become clearer later, right? But the main concept here is this one. for this session, and one of the most important concepts for the chapter is this notion of the differential cross-section. And now I can explain why cross-section. Well, because of the cut. Right? A section is the result of cutting something. Right? Sex. I don't know the Latin, but sec means to cut. So effectively, you're taking this melon, if you like, a unit radius melon. It'd be a very large melon, and you just slice it twice. So this strip here is very, very thin, and that's your solid angle. That's your d sigma, right? And the proportion. I'm not sure if the camera's stopped. Just a minute. So the proportion of your beam going in that comes out, gets scattered into this solid angle, that's your dn, right? And you divide the whole thing by j to talk about unit flux, so unit flux density. Okay, so if it's not so intuitively obvious, you need to think about the nature of this differential cross-section, and the cross-section is a result of cutting the unit sphere twice, getting this very thin slice of melon, right? And then the surface area here along this strip, that's your solid angle, d sigma, and hence cross-section. Okay, so well, I'll run out of board as usual, so I'll stop there.